We're now going to finish off chapter 21 by looking at how magnets can exert forces on each other. We've already discussed Pauli-Abdul rule and the fact that opposites attract and likes repel. Well, magnets also have the ability to interact with internal and external magnetic fields, which also cause forces. And the first we're going to look at is one performed by Michael Faraday. We mentioned Faraday before, but he showed that you could have a force being exerted on a current-carrying wire that was inside an external magnetic field. And so, diagram, we're going to draw this up real quick. I'll do a quick one. So if I have a magnetic field that's here, what I'm going to just draw is kind of two bar magnets, a north and a south pole here. So my magnetic field lines are going across as such. And I'm going to have a current carrying wire, which I'll put in red, going through here. So it's very similar to what the picture we have over here. But the one I want you to draw is the one I'm drawing right here. And so I'm just going to break this off. This is going to be attached to a circuit, but we're going to have a current traveling through it. And we'll have our current traveling into the page, away from us. Now, as of right now, if that current is traveling through, we know that it generates a magnetic field. And by using a right-hand rule, we know, and I'm going to put this in orange, that it's going to create circular magnetic field lines around it. And according to our right-hand rule, it's going to go in, from our vantage point, a clockwise direction. Okay. Now, through interactions of these two magnetic fields, what we find is that there is a force that is going to be generated on that current carrying wire. And that force is going to go, in this case, I'll put it in a blue pencil, that force is going to be down. Over here in this diagram, and I'm going to zoom this in just a little bit. So you can pause and make sure you have that diagram, but I'm going to zoom this in now. What we have is our current's coming up like this. Our current's coming in here, going down. So my current is traveling in this direction. Ooh, wow, hang on. I need to back that up. I'm not exactly 100% sure where we ended up, but let me try and get this back. Oh, there we are. Okay, sorry about that. I kind of jumped all over the place. Let's try that again. So current traveling in this direction. So it's going to generate a magnetic field, which I'll put in purple, that is circular. That is doing that. And so what we find is current's going down. This force is going to cause that to go in. If we switch to the direction of current, the created magnetic field will switch directions, and that'll cause that force to go out at that point in time. And I'm going to try and have this demonstration ready so you can actually show you in person tomorrow in class. So it's not just you're not taking my word for it. You can actually see this work. And I have a video attached where a guy has actually done it with a giant external magnetic field, and you can really see it jump. The one that I can do isn't quite as impressive. So, but this is a combination of the external magnetic field and then the magnetic field that's created by our current carrying wire. And that causes a force to be there. Now, the size of that force can be found by taking the equation. Force is going to be direct proportional to the current going through it, because that's going to generate a larger magnetic field. The length of the wire that's inside the magnetic field, and the external magnetic field itself. Okay. Now, there is a little tidbit on here, because remember I said that the magnetic field generated is always perpendicular to the current carrying wires. Well, that perpendicular thing comes back again. And so we're going to throw on a little sine theta here on the end of this. Okay. You aren't ever going to have to know that, because we're always going to be dealing with either always going to be perpendicular or parallel. But just remember that if it is perpendicular, when the magnetic field and the current are perpendicular, you get a maximum force, because then sine of 90 is 1, so it'd just be ILB. But it's going to be 0 if we were to rotate this wire up here, up top, if we were to rotate that and make it parallel to the magnetic field, there wouldn't be any force whatsoever. Okay? So you don't really have to remember that too much, other than the fact that you will get a maximum force when it's perpendicular, and a minimum force, 0 force, when it's actually parallel. Now, this force will also be exerted, a magnetic force will also be exerted on a single charge. Because if you think about what is in a current carrying wire but single moving charges, just a bunch of them. So if we go with just one single charge, then we can find that there's a force acting on that as well. Okay? And tomorrow I will go through in class the right-hand rules in order to find out the directions of these forces. Okay? But the same thing can happen here. But if you look and you can see this equation where we're headed, but if we go with our F is equal to ILB equation, well, remember that current is equal to Q over T. And so if I rewrite this to be F is equal to QLB over T, well, take a look at this section. L over T, distance over time, that's the same thing as the velocity. And so that's how we get QVB off of that. But our single charge will create its own magnetic field as it travels through the electric charges or small magnetic fields and forces. That created magnetic field will interact with the external magnetic field and cause there to be a force between. We can now find the force on that by using F is equal to QVB, and that force is going to be, again, subject to the perpendicular rules, where the fact that if it's perpendicular, you get a maximum, and if it's parallel, you get a minimum or a zero. Now, this also comes into play if we have it moving perpendicular to the magnetic field. Since that force is always perpendicular to the velocity and the magnetic field strength, it'll actually travel in a circular path. And so the magnetic field is going to be equal to the magnetic force is going to equal the centripetal force. So QVB is equal to mv squared over r. And by adjusting for that, this is actually how we can determine what the mass of a proton, the mass of an electron is. Now, just like before, we had the a generated magnetic field, a created magnetic field will interact with an external magnetic field. If you have two current carrying wires, each of those will create its own magnetic field, and those two magnetic fields will interact as well. And so if I have current traveling up in both cases, it'll create its own magnetic field, and these magnetic fields will interact as well using our right-hand rule. Here the magnetic field is going counterclockwise. Here the magnetic field is going counterclockwise. And if you look at this middle section, the created magnetic fields are opposite. So this will cause an attractive force between the two wires. So my current carrying wires who are generating their own magnetic field will cause the two things to attract together. Okay, another picture of it's down here. Okay, and so we use the Pauli dual rule, and again, this is just based off of, we already did this one. If you look at this one, I'll draw the magnetic fields there. And here on this one, magnetic field is going counterclockwise. This one will be going clockwise, and therefore they are the same in between, and that's going to cause a repulsion at that point in time. Now, this is actually how we define what a current is. We find that the force per unit length between two charges is equal to 2 times 10 to the negative 7th times the current in the first line times the current in the second line divided by the distance between them. Okay, and I wrote that as an R. Okay, but that's really the distance between them. You could use a D if you wanted. Okay, and this is actually how we define how big an amp is. Because if you have 1 amp of current going through each wire, and they're 1 meter apart, that'll exert a force, either attractive or repulsive, depending on their directions of current, of 2 times 10 to the negative 7th newtons. That's how we define to be what 1 amp is. Okay? Now, the next thing here is if you have a wire loop, again, I know we're going through this fast, and we're going to talk about it in a lot more detail tomorrow, but again, this is just kind of the rough, quick slam, hey, here's all the info. But if I have a wire loop in between, so I'm going to put that in orange. Well, let's say my wire loop comes up and does this, okay? So that my current, I'll put that in red, comes up like this, goes in, around, down, back out, like that. We know there's an external magnetic field which goes north to south. I'm just going to put in a couple of those. Okay? So put the arrows in. There's my external magnetic field. We know that there's a magnetic field generated around this wire loop. Or sorry, around this current carrying wire. And I'll put another one in over here. Now, if we go with the direction, okay, we're going to find out that because the current is traveling in on this side, it's going to exert a force down on this side of the loop. If we look at the other side, because the current's traveling out, that's going to exert a force up. And so if you push down on one side and up on the other, that's going to cause that whole loop to turn. And this is the foundation behind a lot of our meters that we've used. What you have a picture of here, this is what's called a galvanometer. And what a galvanometer does is it uses this turning effect to measure how much current's going through. It's hooked up to a spring, and I'll highlight the spring. The spring's right here. That would normally keep it straight up and down. Well, the more current you put in, the greater amount of force it's going to cause it to turn. And so the amount of deflection, the amount of force, is going to be directly proportional to the current that goes in. Now, this galvanometer is the foundation for the other meters that we've used in here, the ammeter, which measures how much current. And tomorrow I'll give you how we adjust our galvanometer to do that, and also our voltmeter. Yep. And I'll give you the diagrams to go with that tomorrow. The last thing we want to look at is an electric motor, because the electric motor it culminates this whole thing with this turning effect of a wire loop inside a magnetic field that exerts a force. What you have here is if you are running current through this, okay, you're going to cause a force on this side to push down, a force on this side to push up, and that's going to cause that thing to turn. And if you are constantly causing those forces to go down on the left and up on the right, that'll cause our electric motor to continue to spin. And so this is how we convert electrical energy into mechanical. And I'll show you a couple demonstration motors tomorrow. We can take a look at it and go in more detail. But this is the end of chapter 21. We'll talk about it more tomorrow. So everybody, have a great night. See you later. Bye.